And today we're doing first order linear ODEs. And what it means to be linear is that it would be linear in just the dependent variable y and the derivatives of y, like y prime. And since it's first order, there's only a first derivative. So it has to look like this. You get a function of t times y prime plus a function of t times y equals a function of t. And when you see these, the first thing to try is to think, could I just solve ODEs of this type by reversing the derivative product rule? And you guys remember the derivative product rule? It says basically if I've got two functions f and g, I want to take the derivative of the product, that's f prime g plus fg prime. I think it's nice to know where math comes from, and so if you've never seen the proof of this, the proof goes like this. You say, remember the definition of the derivative? By definition, the derivative of a function is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So in our case, if I have the derivative of f of x times g of x, this is going to be the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x divided by h. And the trick is, you know, I would have never known what to do from here if I hadn't already seen it done. So it's one of those tricks where you just got to remember this one line in the proof. And then the trick is we're going to take the same thing, but in the numerator, I'm going to add and subtract a term that looks like, let me think for just a minute. We're going to add and subtract the same thing, and that's going to be f of x times g of x plus h. So that now my numerator looks like that. Super long and obnoxious, but it means the same thing, right? Same value, because I'm just subtracting and adding the same term. The reason this is such a nice trick is because now, for these first two terms in the numerator, I could factor out their common factor. What's the common factor there? G of x plus h. And then what I'm left with is f of x plus h minus f of x. And then for the second two terms in the numerator, I can factor out their common factor, which is f of x. Okay. Well, in this limit, remember your properties of limits. I can choose to separate a limit where there's a plus sign, and I can also even separate a limit like between factors when I'm multiplying things. And so this is going to be, really obnoxious just to write down this proof because so much of it is repetitive. But you can probably see where we're going here. By using my friendly properties of limits, separating the limits where I need to at the plus signs and the times. What is the limit as h approaches 0 of g of x plus h? That would just be g of x, right? What is the limit as h approaches 0 of f of x plus h minus f of x divided by h? Here's a little hint. Yeah, this is the definition of the derivative. That's what we said. This is what it means to be f prime of x. And then we've got the limit as h approaches 0 of f of x. Well, there's not even an h there. And then what is the limit as h approaches 0 of g of x plus h minus g of x divided by h? Yeah, that's once again the definition of the derivative, but with the function g. And so this is why we say, if I'm taking the derivative of a product of functions, it's something like f prime g plus fg prime. The proof is really not difficult. It doesn't rely on anything that's really tricky at all. The only thing that's a little bit tough to remember is going from this orange step to the blue step where you have to subtract and add the same term. You just have to know what to subtract and what to add to get where we're trying to go. But that's the idea. Any questions? You guys see that in Calc 1? All right. So, like I said at the very beginning, we're going to have these first order linear ODEs that look like this. And we're going to be able to solve some of these by reversing the derivative product rule, which means we're going to see something that looks like the right-hand side of this equation. You're going to see in the ODE something that looks like f prime g plus fg prime. And then we're going to move from right to left. We're going to reverse that derivative product rule to rewrite our differential equation. So in exercise 2, it says find the general solution to the ODE and the particular solution to the IVP, blah, blah, blah. This is what I mean. When I see 4 plus t squared times y prime plus 2ty, this looks to me like that a little bit. It looks a little bit like the right-hand side of the equation in the derivative product rule. Because y could be, g here, and then you see g prime and y prime pop up in the same place. So this would only work if 2t was the derivative of 4 plus t squared. Does that make sense? But the derivative of 4 plus t squared is 2t, right? So that's really convenient. That works out. So this is kind of a special case. It doesn't happen all that often. But that means it's the same thing as taking this product and then taking the derivative. So we can rewrite the left-hand side of this ODE as 4 plus t squared times y. And then we're taking the derivative of the entire thing, the entire left-hand side of the equation. And the right-hand side of the equation is still 4t. So that's what I mean by reversing the derivative product rule. Does that make sense? Okay. Once we get it like this, we just have to take the antiderivative of both sides with respect to t. So to get rid of the derivative, we just take the antiderivative. And on the left side, the derivative and the antiderivative cancel out, and you get the 4 plus t squared y equals, on the right-hand side, what's the antiderivative of 4t? 2t squared plus c. Don't forget plus c. Now I want to solve for y to get my solution. My solution is going to be 2t squared divided by 4 plus t squared plus c divided by 4 plus t squared. And if I want to solve, I mean, this is the general solution to my ODE. ODE. If I want to solve the initial value problem, I got to figure out what is this c constant. And so the solution to the initial value problem would be say that c is 4 plus t0 squared times y0 minus 2t0 squared. So given some initial time and initial value, t0, y0, you should be able to calculate what that constant c is going to be in your solution. So this part is what we call the solution, the particular solution to the IVP, the initial value problem. Okay, so any questions so far? This is, like I said, this is kind of a special case. This is sort of the easiest case. I've got a first order linear ODE. The first thing I'm going to do is check to see if the left-hand side of the ODE looks like a derivative product rule. And if it does, meaning like 2t is the derivative of 4 plus t squared, then I can reverse the derivative product rule. I can take the antiderivative of both sides and then rearrange it a bit. Did I remember to post the Desmos link so you can make direction fields on Moodle? Let me check. Yeah, so if you click direction field generator on Moodle, it'll take you to this and you can type in your ODE. So our ODE takes a little bit of work to make it so you can plug it into that Desmos thing. The little bit of work I'm talking about is like you have to solve for y prime. So this would be like 4t minus 2ty divided by 4 plus t squared. And in Desmos, I don't think it likes to use the letter t. I think you have to use the letter x. So for Desmos, 4x minus 2xy divided by 4 plus x squared. Let's see how that goes. Okay, so in blue, that's my direction field that represents my ODE. And in orange, we got to type out my solution, which is going to be 2t squared plus c divided by 4 plus t squared. And to pick a value of c, I need 4 plus t0 squared times y0 minus 2t0 squared. Nope, that's not right. Minus 2t0 squared.
Is it because you're not using x for your t?
Oh, you're right. Yeah. Thank you. Sorry. These t's should be x's because it's Desmos, and I don't think Desmos always loves the variable t as much as it works with x. Perfect. Okay. So yeah, changing my t's to x's. Now I've got a solution that passes through my green point of initial conditions. Choose any time I want, choose any value I want. I can find a solution. Yeah, my orange curve seems like it does behave according to the direction field everywhere. If you haven't already done this, like while you're checking your homework problems, do it. It's fun. I think it's just nice how it always fits this direction field, but maybe I'm just too easily entertained. All right, so like I said, that's a special case. That was the easiest case. What if we can't just reverse the derivative product rule? Like here, I would need -2 to be the derivative of 1, which obviously is not true, so I obviously can't just reverse the derivative product rule in this example. In this case, we use a method called the method of integrating factors. And the method of integrating factors is not too crazy. All I have to do is multiply the entire ODE, left side, right side, every single term, by mu of t. This is called an integrating factor, and mu is the symbol that just about everybody uses for their integrating factors, and it's mu of t because this can be any function of t. Just a placeholder. We figure out what mu of t is going to be later. But this is my integrating factor, and I can now write mu times y prime minus 2 mu y equals 4 minus t times mu. So I multiplied the entire thing through by mu. And now, when I go to think about reversing that derivative, product rule, yeah. When I think about reversing the derivative product rule here, we need -2 mu to be the derivative of mu. Because the product rule says I need a function times y prime plus the derivative of that function times y. That way it looks like the right-hand side of the derivative product rule. That way we can reverse the product rule. That way we can do it like we did before. So if I need -2 mu to be the derivative of mu, I can write myself a little differential equation. And you can solve this differential equation because it's a separable equation. It's an autonomous first-order equation. But off the top of your head, do you recognize any function mu that might satisfy this? Okay, well, if you don't recognize anything that might fit the bill, what you could do is divide both sides by mu. Remember that mu prime is the derivative of mu with respect to t. and then the right side becomes negative 2. We take the antiderivative of both sides with respect to t. We have a separable equation like this, and then remember the dt's in this case cancel pretty well. You take the antiderivative of 1 over mu with respect to mu, we get the natural log of mu. On the right side we get negative 2t plus c. To get rid of the logarithm, we would want to take the exponent of both sides. And then you can always set the little c that you get to 0 in this case, because remember this mu has nothing to do with my original differential equation, right? It did not exist until we just made it up and we multiplied both sides by mu. So we really just wanted something convenient that fits this description, but it doesn't have anything to do with the physical property of our system. It doesn't have anything to do with our original differential equation. C can be whatever we want, and in that case, we just choose c equals 0 to make it nice and easy. And so all said and done, we choose mu equals e to the negative 2t. That way, mu prime is negative 2 mu. And we rewrite that blue ODE right there, and we can rewrite it as e to the negative 2t times y prime minus 2e to the negative 2t y is equal to 4 minus t e to the negative 2t. And then we are going to reverse the derivative product rule finally. We can reverse the derivative product rule by writing the derivative with respect to t of e to the negative 2t times y. The right side stays the same. Now, take the antiderivative of both sides here with respect to t. On the left side, the antiderivative cancels the derivative, and we just get e to the negative 2ty. On the right side, this is an ugly integration by parts thing where you've got like 4 antiderivative of negative 2t dt minus antiderivative of t e to the negative 2t. It's the second antiderivative that's going to require integration by parts. So the first one is just dividing by negative 2, right? So it would be negative 2e to the negative 2t. So take the derivative of that. Seems right. For the second one, integration by parts tells me u dv is equal to uv minus v du. So let's say the t polynomial factor is going to be u. The e to the negative 2 t is an exponential factor that gets to be dv. So u times v is going to be negative 1/2 t e to the negative 2t, and then minus the antiderivative of negative 1/2 e to the negative 2t. After integration by parts. This antiderivative, by the way, is divide by -2, you get 1/4 e to the -2t. And don't forget plus c somewhere. Been taking antiderivative, so we need one of those. All right, so -2 e to the -2t. I'm counting how many negatives I have. 1, 2 negatives make a positive. So -2 plus 1/4 would be like -7/8. No, -7/4 e to the -2t. The next thing I need is 2 negatives make a positive, so that's plus 1/2 t e to the -2t plus c. And then the last thing to do is just solve for y by multiplying both sides by e to the 2t. And I get -7/4 plus 1/2 t plus c e to the -2t. This is the general solution to my ODE. And if I want to find the particular solution to my IVP, I need to find the value of c that makes all of this work, which is going to be e to the -2t0 times y0 plus 7/4 e to the -2t0 minus 1/2 t0 e to the -2t0. That would be the particular solution to the IVP, given some initial time and initial value. So once again, let's get the direction field for my ODE, which is going to be 2y plus 4 minus x. The solution is going to be -7/4 plus 1/2 x plus c e to the power -2x. And then to find c, this is going to be e to the power -2 x0 y0 plus 7/4 e to the power -2 x0 minus 1/2 x0 e to the power -2 x0. Okay, how do we do? Not good. Not good, because my solution is not passing through my initial points. And it doesn't seem like my solution even matches the slope field, really. The direction field does not agree, so that's not good. Some bad signs in here. Do you guys notice any mistakes that we made along the way?
Did you, because at one point you took out the 4 for the 4 minus t, did you ever multiply that back in?
Yeah, you're talking about like right here maybe, where I had 4 minus t e to the -2t, and I split that up into 4 times e to the -2t, and then -t times e to the -2t. I think we kept that correct. Oh no, we didn't. Oh yeah, we did. Yeah. So this became this term, and this one became that after integration by parts.
Oh,
Did anybody else notice a mistake along the way? I'm going to say this every single day in this class this semester, but these problems are so long that it's incredibly easy to make a little mistake, right? Like, in a problem like this, where you've got to come up with an integrating factor, finding the integrating factor involves solving a small separable ODE, multiplying by the integrating factor, reversing the derivative product rule, taking an antiderivative, using integration by parts, combining it all together. There's just so many steps that it's like really easy to make tiny, tiny mistakes. And having made a tiny mistake, it really just goofs up the whole problem.
The c would be divided by e to the negative 2t, wouldn't it? Would it not be?
Oh, you're right. That should be a positive. Yeah. Boop. Thank you. Very good catch. Yeah, that should be e to the positive 2t. Let's see if that fixes all of our problems. It does. Look. So our solution now goes through our initial conditions, that green dot, and our solution is parallel to all of those line segments. This is also kind of a neat problem because it's got one end behavior if I have a certain set of initial conditions, and if my initial conditions start a little bit lower, then it has a completely different end behavior. It goes from like up to down. And I bet there's some kind of point right there in between where if I were to set x0 equal to maybe 0 and this to negative 1.75. Yeah, I would get that. Get a straight line, but only if you're right there on the edge. If you tweak it at all, then you go exponential. Okay. All right, so sometimes it happens that it's not possible to explicitly take an antiderivative. And so we'll talk really quickly about the explicit formula that you can use to solve these and where we get it from. Because consider this. I've got some first order linear ODE. And every first order linear ODE has to look like some function of t times y prime plus some function of t times y equals some function of t. So take this and divide the entire ODE by the function capital P of t, and you would get something like this. Where the function here, multiplying y, would just be capital Q of t divided by capital P of t. And this little lowercase g of t function would just be capital G of t divided by capital P of t. So anytime I have a first order linear ODE, I could always just divide by whatever is multiplying my y prime in order to have just y prime by itself. Something I could choose to do if I just want to rearrange the ODE. So whenever you see this, as it appears in my notes right here, that's what I mean. Any first order linear ODE may be written like this, if I just divide by whatever is multiplying y prime. And if I do this, then I would think to myself, I want to introduce an integrating factor, call it mu of t, where I multiply this entire equation by mu of t. And we want to find mu of t so that mu prime of t is equal to mu of t times f of t. So if I divide both sides by mu, I get 1 over mu d mu dt is equal to f of t. And then I take the antiderivative of both sides with respect to t. And then this antiderivative of 1 over mu becomes the natural log of mu. And on the right side, I get the antiderivative of f of t dt plus a constant. Well, I don't need the constant yet because I haven't taken the antiderivative yet. And then the next thing is, well, what if I write this as the exponential of this antiderivative of f of t dt? And I can't have a plus c and then just set it to 0, because c can be whatever we want. This was a made-up function, the mu function, the integrating factor. So it doesn't have to be anything in particular. We just set c equal to 0, make it easier. That's how you end up going from this to this, right? We've explained part of this formula, that my integrating factor is always going to be the exponential of the antiderivative of the function that multiplies y if I divide by whatever is multiplying by y prime. What about the rest of this, right? In the rest of this, we've got this side of the equation, which can be reverse product ruled into mu of t times y. And the right side of the equation is now mu of t times g of t. And taking the antiderivative of both sides gives me mu of t times y equals the antiderivative of mu of t g of t. And if I divide both sides by mu of t, I get this. I can't cancel out those mu of t's because one of the mu of t's is obviously in the integrand. The last kind of step here is to say I'm going to set the lower bound of this integral to my initial value for time. And I'm going to change the variable I'm using for integration just to be super clear. Let's call it s instead of t. And then because I could choose a different time value to start my integral at, right, later or sooner or whatever, I do have to include a little constant. And solving for that constant is going to be the problem of the initial value problem, figuring out what that c is. But these are formulas that we can use then, These are formulas that we can use to solve any first order linear ODE. Oh yeah, did I put the plus c in the wrong place? Kind of. I need to be more specific because the divided by mu of t, that applies to the c as well. C should be divided by the integrating factor. Okay, so if you wanted to, you could just memorize these formulas instead of having to think through how to find the integrating factor, instead of having to think through how to reverse the derivative product rule. That would be a totally valid thing to do, is you could just put your ODE into this form and then apply these formulas. It's kind of like back in your 9th grade algebra class, you learned how to factor quadratic equations, and then later your teacher taught you the quadratic formula and said you don't really have to think about factoring anymore, you could just remember the formula and then apply the formula. This is the same exact thing. You could think for yourself, or you could just memorize that formula, and I don't care which one you choose. You just got to do one or the other. But just like just like whenever we had the quadratic formula, sometimes there is quadratic equations that you had to use the quadratic formula for because they weren't easily factorable. That can happen sometimes with these first order linear ODEs too. Like this one honestly looks very benign. This one doesn't look like it's very difficult on the surface. It's only got some constants, a t, like it's fine, it's whatever. But what happens? If I try to solve this, I don't like memorizing formulas, so I'm just going to jump straight into the integrating factors idea, which is to say 2 mu y prime plus mu ty equals 2 mu. Sorry, that should be a mu. And I need mu such that the derivative of mu I should say the derivative of 2 mu is mu times t. And since, you know, homogeneity, I could just divide by 2. I could say this is 1/2 mu t. If I divide both sides by mu, take the antiderivative of both sides with respect to t, I don't need the c because this is just an integrating factor. I can set c equal to 0. Then take the exponent of both sides. I get e raised to the power 1/4 t squared. Nice. So back to my equation, and I have 2 e to the 1/4 t squared y prime plus e to the 1/4 t squared times t times y equals 2e to the 1/4 t squared. And on the left side, we can reverse the derivative product rule and write the derivative with respect to t of 2e to the 1/4 t squared y. On the right side, 2e to the 1/4 t squared. And now I would need to take the antiderivative of both sides of this equation. And on the left side, the antiderivative just cancels out the derivative. No issue. On the right side, my problem here becomes this. How do I take the antiderivative of e to the 1/4 t squared? That's one of those you can't do it, right? If you have like e to the x squared, there's just not a closed form antiderivative for that. None of the strategies you learn in Calculus 2 work, but also it's been proven that there are no strategies. You just cannot write it down as a combination of elementary functions. That isn't to say it's not analytic. Like it's a nice analytic function that has a power series. I think it's even an entire function, meaning like the radius of convergence of the power series is infinity. It's a really well-behaved power series. So it's an analytic function, but it's just not an elementary function. You can't write it down in terms of polynomials or exponents or logarithms or sines or trig functions or whatever. So we got to leave it alone. If that happens to you, you get one of those antiderivatives that you just can't crack. You just leave it alone. And that's just is what it is. And remember, we picked up a constant because we took the antiderivative of both sides. And then we write something like this for our final answer. we divide everything by 2, and we divide everything by e to the 1/4 t squared, and we get e to the power negative 1/4 t squared, antiderivative of e to the 1/4 t squared dt, plus c times e to the negative 1/4 t squared, and I forgot, well, I could divide c by 2, but it's still just an arbitrary constant. Then we're going to label the lower bound and upper bound of my integral as the initial value and the value of t we're concerned with, and then I ought to change the variable of integration from a t to a lowercase s, because that's best practice for keeping your integration variable separate from your independent variable. And there you go. So you will get a different value of this integral depending on the initial time you choose, but that's up to the initial value problem to determine what value of c is appropriate to account for that. So believe it or not, you can still check your answer in Desmos. To check your answer, let's solve the initial value problem really quick. We would just need 2e to the 1/4 t squared. Actually, let's get rid of the 2's. Divide both sides by 2. And then, so we write c e equals e to the 1/4 t squared. Except this is going to be in Desmos. So remember that the t's are going to become x's and that we're using initial values, minus the integral from the initial value t to the final value t of e to the 1/4 s squared ds Cool. I think that should do it. So in green, that's my general solution, and in orange, that's my particular solution. Let's see how it stacks up. Man, all of you guys are sick today, aren't you? All of them and you. So it's going to be 2 minus xy divided by 2 for my direction field, for my ODE. And then for my general solution here, I'm going to write e raised to the power negative 0.25 x squared times integral, which you can get an integral in Desmos using int, just the letters int, that does it, from x0 up to x of, oops, I put my integral in the exponent, don't want to do that, of e to the power 0.25 s squared ds plus c e to the power negative 0.25 x squared. And now I need to figure out what is c. C has to be e raised to the power 0.25 x0 squared times y0 minus integral from x0 up to x of e raised to the power 0.25 s squared ds. Interesting. I hadn't thought about this before, but what am I integrating from? I'm not integrating up to t because this is an initial value problem, so I replace the t with t0. And then with the bounds of this integral being the same, that whole thing is just 0. So this should work if I just forget about that. I don't need an integral whose bounds are exactly the same, and voila, it does work. And it's pretty neat. And again, this orange curve will graph on Desmos even though it contains an integral in there. It'll still work if you make the only variable the upper bound of the integral and then you use the variable s inside the integrand. But sure enough, this is how you check your work. It passes through the initial conditions. It meets the field lines. Any questions about doing this one? So even a really, really, really super stupid easy looking ODE can still have a really nasty solution. It's the unfortunate truth here. We're making good time. We've got 20 minutes left, and this is my last problem to show you. An ODE is called a Bernoulli. That should be an N in there, Bernoulli. Like the mathematicians. There's several Bernoullis. An ODE is called a Bernoulli ODE if it can be written in this form. So this looks a lot like a first order linear ODE. The difference between a first order linear ODE, which would look like this, and a Bernoulli ODE is that in a Bernoulli ODE, you're also allowed to multiply that term on the right-hand side by y to the power n, and n can be any real number. If n is 0, y to the 0 power would be the number 1, and this would become a linear ODE. If n is equal to 1, well, then you could subtract f of ty from both sides, and then divide both sides by y to the n, and it would become separable. For every other value of n, the way you solve a Bernoulli ODE is by making this substitution. So in exercise 7, find the general solution to the ODE and the particular solution to the IVP. This is like almost first order linear, except I've got y to some power at the end. That means it's a Bernoulli. And I can solve a Bernoulli ODE by making the substitution u equals y to the power what?
Would be y to the negative 1.
Yeah. Because the n, y to the n power, is 2. And this is u equals y to the power 1 minus 2. So I need u equals y to the power negative 1 for that substitution. Okay. To make the substitution, I've got to figure out what is the derivative of u with respect to t. Right? What is u prime? And the derivative of u with respect to t is going to require the derivative chain rule, because u is 1 divided by y, or y to the negative 1 power. Well, the derivative of y to the negative 1 power would be negative y to the negative 2 power. But because y itself is a function of t, I also have to use the chain rule here and say multiply times dy dt. We don't know what function y is, but we do know y is a function of t. And so we should say u prime is equal to negative y to the negative 2 times y prime. Or another way to say this is that y prime is equal to negative u prime y squared. So let's see how this works. Where I have my ODE, let's rewrite this as negative u prime y squared. Maybe I should write negative y squared u prime. And then plus 1 over t times y equals ty squared. What do you think I should do next? Okay, next, all three of these terms have a y in them, but we're going to go ahead and divide the whole thing by y squared. If I divide this entire equation by y squared, I get negative u prime plus 1 over t y to the negative 1 power and t. What should I do to replace y to the negative 1 power? Yeah, that's the definition of my u, so I could just replace that with a u. And now, what's great about this is this is first order linear in u. So now we can solve a first order linear ODE, which is comparatively nicer. And for this to really work easily, I might check and say, is 1 over t the derivative of negative 1? No. Crap, so I have to use an integrating factor. Okay, so let's pop in that integrating factor, you know. Don't get your mu's and your u's mixed up. And we need mu such that the derivative of negative mu is equal to mu times t to the negative 1 power, or mu over t. Not 100% sure what that would be, so I'm going to just solve this ODE right quick. We write it as a negative 1 over mu d mu dt is equal to 1 over t. We take the antiderivative with respect to t on both sides, and I get negative natural log of mu is equal to natural log of t plus a constant, but I don't need the constant. So I take e to the power of both sides, and what I get is 1 over, yeah, I don't know if this makes sense, but with that negative right there, that negative is like, I'm going to zoom in for you. When I have a negative in front of the natural log, that's the same as 1 divided by this natural log. No, it's not. I'm thinking it's the same thing as the natural log of mu to the negative 1 power. That's a property of logarithms. Whatever constant multiple you have out in front of the logarithm, you can shove it inside the logarithm and make it a power of the thing. So that's what I did. Took the negative 1 out here, put it inside the logarithm. Now if I take the exponential of both sides, that cancels out the logarithm, and I get mu to the negative 1 is equal to t. Or, since these are just reciprocals, mu is equal to 1 over t. Oof, okay. So we found out a t that's going to work. Or sorry, we found a mu that's going to work. And so let's go ahead and rewrite my ODE again. And rewrite it as negative 1 over t u prime plus 1 over t times 1 over t is 1 over t squared. U equals 1 over t times t is just 1. And the left-hand side, I can reverse the derivative product rule and write the left-hand side as just being 1 over t times u. Sorry, the derivative with respect to t of 1 over t times u. And on the right side, I have 1. Now, we need to take the derivative of both, sorry, the antiderivative of both sides with respect to t. On the left-hand side, the derivative and the antiderivative cancel. On the right-hand side, the antiderivative of 1 is t plus a constant. And then multiply both sides by t, and we find that u is equal to t squared plus ct. But remember, we need to go back to that Bernoulli substitution, right? Where we said, I don't want to solve for u. That was just a convenient substitution. U was equal to y to the negative 1 power in my original substitution. And so this means y to the negative 1 power is t squared plus ct. And if I take the reciprocal of both sides, y is equal to 1 divided by t squared plus ct. That is my solution. Whew. Lots of steps to these differential equations problems, aren't there? So to recap, you notice it's a Bernoulli ODE, which is a lot like a first order linear, except you have some power of y on the right-hand side. Then the Bernoulli substitution is u equals y to the power 1 minus n, where in this case n was equal to 2, and then you find out what is u prime, using the derivative chain rule. You use that then to substitute in for y prime, and then you've got to divide by some power of y to get your equation all in terms of u's. And when you get to this point, it should be first order linear in u. If it's not, then you've made some mistake. Once it's first order linear, then you solve by finding an integrating factor, taking the antiderivative, blah, 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 blah. Okay, let's check our work. Let's pray that we got it right. We got ty squared minus y over t. Oh, thanks. xy squared minus y over x. So the blue is the line segments for my ODE, my direction field. My solution is 1 over x squared plus cx. And then I find the c by taking, we gotta find the C. Gotta find my particular solution by solving for C. It would be 1 over y0 is equal to t0 squared plus ct0. So 1 over y0 minus t0 squared divided by t0. Or in other words, 1 over y0 t0 minus t0. Nope, did I try to oversimplify that? Oh, I'm using t's instead of x's. Come on. Every time. There we go. Does it work? No, it doesn't. It's broken. So this is what it looks like to get the wrong answer, right, in Desmos. It actually tracks with my initial conditions, which I'm amazed by, but notice it doesn't go through the direction field. So the direction field should be xy squared minus y over x. Xy squared minus y over x. Yeah, that should be right. So we have the right direction field. So we made a mistake solving for the general solution, because my IVP is correct, right? It's going through the initial value correctly. We just made some kind of mistake in solving for the general solution. Do you see any mistake? Oh, I see a mistake. That should be a negative, right? Because it should be negative 1 over t times u. So negative 1 over t. Let me see if that negative does the trick. It should be a negative here. And then it should be a negative here. And then it should be a negative here. And here. And here. And here. And here. So I should just put a negative in front of my solution. And that means I need to also put a negative here in front of this y. Does that work? Yeah. Okay, now it works. That's how it should look. Cool.